Okay, I think the recording must have begun now. Thanks again for reminding me about that. Yeah, so sort of, so we have studied, discrete time continuous models, right, of this form. And we sort of, discovered that in systems that exhibit non-overlapping generations, there are many, many interesting possible dynamics, like oscillations and chaos, even when the system is deterministic, and even when there are no external forcings that are random or seasonal, right? And then we also looked at continuous time models, okay, and then we looked at their properties, right? And one interesting property of these systems was the possibility of multiple stable states. Okay, you remember this, right? So, for example, we studied this model of harvesting or grazing, right? And then we looked at the equilibrium population density. It had this behavior. Okay, it had this interesting behavior, right? Where between conditions, let's call this C1, let's call this C2. Okay, between these two conditions, C1 and C2 of some environmental parameter, in that case grazing rate. Okay, what was very interesting was that system could have had two possible stable states. Okay, what is this intermediate line? That intermediate line was very important. It showed that if you are above this intermediate line as your initial condition, eventually the system will reach the upper stable state at the high density of population. Whereas if you were to the sort of to the other side of this dotted line, the population will reach this lower equilibrium. So what is interesting here is that in this case, the grazing rate is same for both of these outcomes, this and this. Okay, the only difference was that the initial conditions were different. One on the one side of the equilibrium, other on the other side of the equilibrium. Okay, and depending on the initial value, system could reach one of the two possible equilibriums, and this is what we called system with multiple stable states. Of course, in this very simple case, we only had two stable states. It's also called bistable system, example that we have here. Okay, and this specifically, we studied this in the context of grazing, whose equation was of this form. So in the absence of grazing, the system will reach carrying capacity, right? Okay. However, in the and there was, if we choose Holling's type 1 or type 2 or type 3 functional responses, then we found that we can have this, bistability. Do you all remember these results? This was also and then I had also asked a follow-up question in the assignment on this. Before I go there, I want to make sure all of you remember these results and make sense. Okay. And there were several implications of such a system, right? So what were the implications? Let's look at the implications. Let's revise. We have discussed this in the past. Let's look at them. The first one is, now consider this scenario where the grazing is slowly increasing over time. Okay. And then let's say initially you had zero grazing, therefore a very high, high value of population density. Okay. In fact, this will be close to K here. And then it, because of the increasing in grazing, you would expect that system will slowly follow this trajectory, right? Okay. So if I were to now plot as a function of time, x, okay, how will that look like? Up to some point in time, it will look like there's this gradual change. However, when C reaches this point, C2, what will happen? There is an abrupt shift in the state of the ecosystem. Okay, and then it continues that way if you keep on increasing it further. Is that right? So one implication is that of abrupt transition in a system. But what is so surprising about this, or what is so interesting about this, is the following: that we had an abrupt transition, although driver itself was changing gradually, right? For example, if I were to also plot C as a function of time, that's just increasing. Even if it's increasing in a linear fashion, the system responded in an abrupt or non-linear fashion, right? So that's what makes this very interesting, because there is nothing about the driver here that sort of is abrupt, but the response of the population is abrupt. So the first implication is you can have this drastic and abrupt response of the ecosystem, right? Now, what's the second implication for this? What other implications are there? That's to understand that, let's say now we have noticed that a system has undergone a collapse, right? Now let's say we now try to reverse this now, right? So what does it mean to reverse? Let's say we now we have been increasing C over time, and we have seen that, let's say, system has now collapsed. Okay, there's a collapse of the system, right? But the C has increased. Now let us say we have decided, okay, let's stop the grazing in this place. Now, therefore, let us, of course, nobody can suddenly stop. Let's say you begin to slowly reduce the C. So let's say this was, let's say, C2. And then you sort of have overshot that a bit, and then we begin to reduce it. So what do you expect to happen? Let's go back here. Let's say now we have begun the reverse trajectory. Let me plot that with red line maybe. So let's say I now start doing this. So what do you expect to happen? Will it go back like this? Will the system jump back to this? No, so it won't, because it's in this stable state now. Okay, and it will continue in that state, right? To continue until you reach C1. Only when you reach C1, you can see a reverse abrupt shift. Okay, what this means is that you have to come back, you have to reduce C to a substantially smaller value. Okay, and only then you actually will come back like this. Okay, and that is called hysteresis. Okay, is that fine? Now, what is the implication of hysteresis? Hysteresis implies that it is difficult to reverse abrupt or reverse ecosystems or populations to their previous states. Do you see Does that make sense? Do you all agree with this? This is such a revision of what we did long back. Any questions before I go forward? Is this fine?
Sir?
Yeah.
With respect to the x versus t plot that you drew for the second part,
Mm-hmm.
it will not be symmetric, right? Like because the the rise for the second part is going to happen at C1, which is going to be at a later time, right?
Yeah, you're right. So this was C2. Let's say you reach C1 somewhere here. Okay. So this is C1. So this is where we cross C2. You would expect that by coming back here, you may expect system to recover, but it doesn't happen. You have to go all the way down here. Okay. So this is, let me use a different colors. This is C1. This is C2, which is sort of roughly what I am trying to represent here. Is that fine? So when you cross C1 here, there is this shift. We have reached C1 in terms of the parameter value. Oh, sorry, is that what I called C2? Sorry. And then this should be C. At this point of time, we have reached C. Yeah. So if it was symmetric, it should have started recovering from here only. Whenever C had hit C2 again, right? Somewhere here.
Yeah, and I also meant the symmetric part with respect to the fact that between the C2 to C1, right, for the second half, it'll be like slightly increasing, right? So that part also will be a little different from the left side of the curve.
I mean, the decay, the trajectory of decay and the trajectory
Yeah,
of recovery will look different.
yeah.
Possible. Yeah. Of course, my drawing is not so good to distinguish those. It anyway looks bad, and you can say they're different. You're right. There is no need. The exact features of the transitions, may differ. That's good. Okay. Any other questions? Okay. This is just a revision of what we had done. Okay. Now, there is a very interesting concept I want to introduce you to today. Okay. Which is called that of which actually was covered in the assignment again. So this is again a revision. It's called landscape potential. So this sort of borrowing ideas from the physics here, but with some subtle differences. The idea is as follows. Okay, so now think of two types of scenarios. Okay, so this is the let's write some general graphs here. Okay, so this is the ecosystem driver. And this is the ecosystem state X. Let's consider this extremely simple scenario of ecosystem state changes linearly with driver. Another case where we have this what we had by stability. Okay. So the idea of potential is as follows. We can think of this system as having one minima. And this minima, there's something called ecosystem potential that we denote by U as a function of X. Okay. And this minima corresponds to the stable equilibrium for any given value of driver. Okay. So as the driver changes, this potential landscape minimize changing in location. This is this is, you can think of this as some driver value 1, driver value 2, driver value 3. So as the driver values are changing, this minimize changing the location. And as a consequence, we have this, in this case, specific case, as driver is increasing, the minima is reducing, and that captures the fact that the stable state is reducing. So you should think of the ecosystem as some kind of a ball that is sort of rolling in this kind of a in this kind of a landscape. Okay. and the ball will reach the minima of this landscape. Is it fine? So this is the picture. If this picture is true, how will the potential for this look like? How will the potential landscape for this will look like? Let's consider for this point, this value of driver.
It will be like one valley there.
Valley where? It will be like, are you saying, okay.
For the
like
monostable one, like we
No.
have.
It will be a W.
W, yeah.
It will be like a W, no? Okay. Why so? Because for this value of driver, there are two stable states, and which are different values of x, right? So if this is x, and this is the potential, okay. So if this picture is true, what we expect is something like this. So this corresponds to one stable state of x. This corresponds to another stable state of x. And the way I have written, is that this is the high population density state. This is the low population density state. Okay. And if you began your sort of moving the ball on this side, I'll just remove this. Okay. The remote on this side of the valley, it will come to this stable state. If you start off on this side, you come to this stable state. Is that right? Okay. So if you're looking at the bistable system, this is the way the potential will look like. Bistable systems will have bistable potential. Okay, that's the basic idea. Now, this is not just an idea. So in fact, as I sort of, you may have discovered, in the context of assignment number 3, if I'm right, it's actually mathematically possible to define this in the following way. Where x dot is equal to f of x was the dynamical equation, and x0 is some arbitrary location. Okay, it doesn't have to be initial location, it's actually any arbitrary location. So if it turns out that if you define u of x this way, it actually has these features. So whenever the stable equilibrium, there are two stable equilibrium, this u will actually have two minima. Okay, this is something I had asked you to actually observe by plotting this. Did all of you get this, by the way?
I didn't.
Yes, sir.
Yes, sir.
Was there anybody who had difficulty with this assignment question?
I did not get it.
You did not get this?
Yeah.
Okay. Do you know why?
I should go back and check.
Okay. Yeah. So it's basically, if you just have to do the integration, you can use, I had told you can use Mathematica, right? You can use Mathematica or any such to do integration, and you will find that this u of x has this mapping between the dynamical equilibrium and this landscape potential. No, it's not just, it turns out that it's not just hypothetical. This, you can actually do some additionals. You can actually say a few things mathematically, which I will not prove here. Okay. Okay. There are actually several, once you define this function u of x this way, you can actually mathematically prove the following. Okay. Extrema of u of x. Do all of you understand what is extrema of u of x? Extrema means either minima or maxima. Correspond to equilibrium of the dynamical equation. So So just think about this, whether it makes sense intuitively or not. What does equilibrium of this correspond to? Equilibrium are given by roots of f of x, right? Okay, wherever f of x is 0, those are the equilibrium. And what this is saying is that with this definition of u of x, the roots of f of x basically transform to extrema of u of x. Okay, meaning a root of this is either a minima or a maxima. Okay, in u. Again, I'm not going to prove it's like these are all fairly straightforward calculus that one can do. And the second thing that you will notice that the more specifically, minima of u of x correspond to stable equilibria. Okay, this is what, so these are the two things I was hoping that you will actually sort of arrive at in that assignment by visual inspection. I was not expecting that you will make any mathematical proofs of this because I had given you two types of models, one having this left-hand side kind of equilibrium structure, the other having the right-hand side bistable equilibrium structure. And if you calculate u based on this formula, you would have found these two things. And what I was expecting is that you will arrive at these two conclusions. Extrema of u of x actually correspond to equilibrium of the dynamic, I should say equilibria of the dynamics of f of x, and moreover, the minima of f of x actually corresponds to stable equilibria, and that actually nicely fits with the idea of a ball rolling in the landscape. And you know what happens to a ball rolling in the landscape? It sort of stays, eventually settle down at the minima, right? So this is actually a very useful interpretation. It's not just a useful interpretation, it's also a mathematically accurate interpretation, at least for one species models. One species dynamical model is actually a very accurate description, mathematically accurate description. Okay, now there is actually also a third point, which is interesting, which is the following. You can actually prove it mathematically. Given we have given this dynamics, right? X dot is equal to f of x, right? So what happens to x as a function of time? This is time. This is x. What happens? It reaches some value, right? And typically these are the stable equilibrium, right? This is what happens, x as a function of time, if you start with some initial condition. Now here is something. What happens to u as a function of time? What do you think should happen to you, by the way? If you go back and if this ball rolling in a landscape is correct, what should happen to you? Let's look at this picture here. Let's look at the left-hand side picture. Let's say I start the ball somewhere here. It will eventually come down to the bottom is what we're saying, right? What's happening to you as a function of time?
It
Remains
decrease
the
and then
same,
stay
no?
constant.
Sorry?
Remains the same. It's not a function of time, right? U?
It is
But x is changing as a function of time, right?
Decrease till x stabilizes.
Decrease till x stabilizes.
Yeah.
Okay. So you're saying you will decrease because x is because the ball is coming towards this, x is changing. Consequently, u is changing, right? And in fact, you can see that the u is actually decreasing. Does it make sense, Amir? Do you agree with that?
Yes.
So u actually is decreasing to some value. So in fact, it's actually possible to show mathematically that du by dt is negative. Okay, it will be 0 if we start at the equilibrium value, but it will be in general negative, which also perfectly fits with our intuition that it's a ball rolling in a landscape. Okay, now here is my question to you. If I start the ball here, can it cross the equilibrium and come here and then come back?
It depends on the values that it can take, no? The x values.
No.
It depends on which value, sorry.
X values, if that point is somehow jumped.
Let me ask you a question in terms of f, okay? there you have better intuition. Let me ask you the following. Let's say if this is X and this is F. Okay. F on the X-axis, Y-axis. Okay. Let's consider hypothetical function like this. Okay. Let's say if I start the population at this value, where will it go? To the right or left?
Right.
Do all of you agree? Because here the growth rate is positive, it should go towards right. Will it cross this equilibrium?
No. No.
No.
It just goes there, right? Will it cross and come back?
No.
No.
It just goes there. Now, coming back to potential. What is this? I told you this is equal to basically equilibrium, right? Stable equilibrium. This point is stable equilibrium. So will it cross and come back?
No.
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 Right? So it cannot, right? So again, going back to this, du by dt is always negative. Because of this, can it cross and come back? If it crosses, what happens to du by dt? The u will increase with time, right? So again, that's not possible. So it actually, the way this moves, it just comes here and then just asymptotically reaches the.
I have a doubt.
Yeah.
So when do we see damped oscillations?
That you see in two species systems.
So it's not possible here for it to cross like the magnitude.
No, it's not possible. Yeah, which is why this is not the physics potential. Okay. So this is why it's not same as the a true ball rolling in a valley. Okay, that's where it's slightly different.
Mhm.
So this valley is a bit different. You should think of this valley as a valley with high amount of friction. Okay, and when you have high amount of friction, can you have oscillations? You just reach the equilibrium. It's called overdamped scenario. That's what this is actually. That's a good question. So this potential is actually not the physics potential where you can have damped oscillations. You can only have trajectory that goes towards the equilibrium value. Okay, so this is another so this is sort of following up on the assignment we had done. Okay, in one of the assignments. So why am I telling you all of this? Okay, because it's actually, it turns out it has some. Oh, what happened? What is this? Some moving line. Okay. So why am I telling you all this? Okay, now that I have covered something about this, let's go back and ask some ecological questions.
I had it out.
Yeah, sure. How do I get rid of this line? Yeah, go ahead, please. Yeah.
So with respect to like these landscape, right? Like if it's
Excuse me, sorry.
you showed us one of this potential, right? Like the W potential. So if I start from one of the wells, like towards like if I start from that right well at a much higher height, it has the ability to cross the unstable barrier depending on the height of the barrier, right? In between.
Are you saying if you start somewhere here?
Yeah, exactly.
As we just showed you, du by dt, of course, I did not mathematically prove this, so this is always going to be. You have to trust me on this. You have to trust me when I say that this is math. This is a mathematical statement. You cannot. No, this is a mathematical statement. In fact, the proof is literally 3-line proof, but I don't want to do it. Do you actually want to see the proof? I mean, does that make you better? I don't know why these things are floating around.
Not exactly the proof. It's because I remember there was some landscape function, like landscape potential example given in terms of some cell, like I think some disease cell or something, and it has the ability to change from one phenotype to other. Like there's some Waddington's epigenetic landscape, right? So there they say that you have the ability to cross one potential, like the potential barrier. So I was just wondering if this particular situation, this particular landscape that you have defined fits those situations or not.
No, I don't. I think these are different. Okay. So let me. They're different in two ways. So this landscape here is not energy landscape. Okay. Are you able to see this, by the way?
Yes, sir.
Are you able to see my own notebook or something else? I don't know what I
Yes.
actually shared. Okay. Let me share again. Oh, I think I had shared my entire notebook. Okay, entire screen. Okay, this is better. You're able to see this now. Okay. So this is okay. Here is one very important thing. So what is the meaning of this potential landscape? It actually has no meaning. So if you are thinking of energetics of the type that a cell is required to cross a barrier, right? It is not anything like that here. This is really purely a mathematical construct. This has no physical or ecological meaning. Actually, something you should think about if there is any. Okay, so therefore you have to think differently about this function. This is also called Lyapunov functions in mathematics literature. Lyapunov functions are basically artificial constructs. They have no they don't necessarily always have a physical intuition behind them, and the only physical intuition that you should follow are these three. Extreme of Vx correspond to equilibrium of the dynamics, minima are the stable equilibrium, and the du by dt always increases. Now imagine a system. I think the confusion is happening for the following reason. Imagine a system where the energy is, let's think of physics systems, right? Imagine a system where the energy is conserved. Okay. If the energy is conserved, if I start the ball here, what happens to it? When it comes down here, what will be the kinetic energy? It will be very high, right? Hello, can you hear me?
Yes, sir. Yeah.
Yeah.
It will be
And
maximum.
then, so therefore, it actually will now go up. It will also cross. It will again go up and come here, right? That's the intuition you have based on the kinetic energy to potential energy, potential energy to kinetic energy conversion. And that is true only if the entire landscape has no friction, right? So the right way of thinking about this potential is that even if you think of it as energy potential, think of it this landscape having massive resistance or friction. Therefore, what really happens is that the energy friction is so high, it just comes here and stops at this point. So these are called overdamped systems. Have you heard of overdamped systems? When you study harmonic oscillators, you should think of these as that, which is why there is no question of being able to cross the barrier. Now, of course, there are ways to cross the barrier. Imagine there was stochasticity, which is the next thing I was going to come to. Imagine there is stochasticity, right? Then that's how things can actually be pushed across the barrier, but not in the deterministic systems. Is that fine? Does that answer your question?
I have one doubt.
Yeah.
Where in the equations do we see this overdamped system, like that property coming about, like when we write the
that takes some effort. I can see the way to one way to think about this is that, so however, how did we write the equation? We wrote the equation this way, right? Yeah. Okay, so x is some state variable, right? Now this is our current equation. Now go back to the physics. How do you write the equation of, and then basically with this definition of u, you can also write this as this. Okay, so this is x dot is equal to minus du by dx. So now for those of you who still remember your physics, do you remember that the force is equal to minus du by dx? Do you remember this?
Yes.
Okay.
Yes.
And then what is force? Force is also equal to mass times acceleration. Do you remember that? So therefore, if I were to assume that the mass is 1 unit, what do you have? X double dot is equal to minus du by dx. Is that right? So this is the physics equation of how a particle moves in a potential. But this is the dynamical system moving in a potential. Do you see the difference between the two? Okay, let me not say m is equal to 1. Let me just keep that. What's the difference between the two? X double dot is equal to minus du by dx is what the physical systems are doing. And these are also called conservative systems. In this system, the energy is conserved. What does that mean? Whatever the initial value of x0 you have, that's always, if you write that as, u of x of, that will be same, that will be this plus the kinetic energy of x of t. Okay. So this gets partitioned into two conservative systems. Basically, total energy remains same, but that will not be the case here. Okay, and moving in a potential landscape like this, but also assume there is a friction. So how do you write friction? Gamma x dot. Okay, so what does friction mean? The friction will increase with the speed. That's the intuition behind friction, right? So this is the frictional force that comes into picture. Okay, and now you can see how to go from here to here now. So ecological or dynamical system models for x dot is equal to minus du by dx. Physics systems over mx double dot is equal to minus du by dx. But if we include physics with friction, this is what you get. Now consider a system with where this lambda is very, very, very high. Okay, so therefore I can now ignore this term, ignore the inertial term. So that's when we have gamma x dot is equal to minus du by dx. And that is basically same as overdamped systems. Okay, I wasn't planning to cover this at all. So, so if you, it's not important for our discussions today. Okay, but since you asked, I said I'll just see how it works. Does it make sense, Amir, now? No, does it make sense or no? But this point about whether they actually get stuck at this point or move around a bit, it's not particularly crucial, by the way. You can sort of intuitively still think about the regular physical system of with friction, where they also sort of slowly damp down and oscillate to the equilibrium. That's also fine, but don't think of them as frictionless systems, because in that case starting here will take you there, right? Don't think of it that way. Okay, so now let's go back and ask some ecological question. Okay, which is, if you have these systems, right, with more broadly biological systems with, and of course there are many systems, cellular systems, genetic systems, many of them which show this kind of bistability, with bistability or multistability. So, and in fact you have read the paper by Martin Schaffer, if I am right? So where you learned problems of eutrophication, which is an abrupt shift, right, of algal blooms. You have read about desertification, right, and collapses in marine ecosystems, and so on. So let's say you are somebody who is at the field station and collecting data. This is time. Let's say you are at some field station, you are collecting data, some state variable x. For example, this could be, maybe if you are looking at a lake ecosystem or a marine ecosystem, you might be measuring species abundances. Okay, let's say you're measuring this. Okay, and then basically, if you wait long, maybe, and if the system is prone to this bistability, over time, what might happen? It might suddenly collapse to this new state, right? And this is one possible scenario that can happen. So as somebody who is interested in managing this ecosystem well, what is the thing that you would like to know? This is a possible scenario. This is a possible scenario. Let's say we are here. Okay. So what is the question you would like to address?
When will the system change if it changes?
When will
The state
the
change.
state, right? Or rather, when will abrupt collapse happen, right? To be more specific.
Does it depend upon the amplitude of fluctuations that the system is having?
Yeah, absolutely. Yeah, it will. Don't you think it will depend on? It probably will depend on, right?
Yes.
It will depend on the amplitude of fluctuation. It will depend on how far, but imagine you have this framework to think about now. So we know that the system has some driver D, and we know that this is the behavior that we think is probably true. Okay. So ideally you would like to know when will it happen is one question. We can begin to ask more precise questions, right? What is this? What are the values of, right? D1 and D2, right? That's another question you can ask. Is that right? Know what are D1 current value of D, you can probably do something about this. But often you don't know what is D1 and D2, right? This parameterization is often very difficult. So what are the questions you might be interested in, if you're somewhere here and trying to manage the ecosystem, what other kind of, questions that may come to your mind, and, how can I, so the question is, can we do some mathematical modeling to address these questions?
Can we say something about the critical slowing down at the tipping point, like where the system is very, very slow dynamics are observed?
Yeah, that's a very, very good point. So, this is something again, we had discussed in the class as a response to a question that somebody had asked. Okay. So I don't know how many of you remember this. So I will summarize this if people don't remember. Okay. So any other questions before we go there? Hi, I could not hear.
How do we know what to measure?
That's another great question. So how do we know what to measure? Let's say you have the measurement of X as a function of time. Let's say you have that measurement somebody has given you, and there is some automatic measure. That's a question to ask. You can of course ask, can I measure more about other ecosystem processes? Okay, maybe those processes give me some indication of, what might happen, how stable the ecosystem is and so on, right? Okay, so let's try to understand this. Let's try to ask this question and try to address this question. When will this state change? Okay, so to understand this question, we have to go back. Why did I introduce already? We have to go back. We can actually use this idea of potentials. Okay, again, I'm going to explain this only qualitatively without any mathematical proofs. Okay, although if you actually go back to if you go back to but it's possible to provide some intuition behind what's happening. Okay, so somebody mentioned something about critical slowing down, and we had actually covered this in the class in detail. So let's think of stability. So when will a system collapse to other state? When the stability of the current state reduces, right? Okay, collapse happens when the stability reduces, right? So basically, if we have some way of measuring, stability, we can say something about possibility of what it is, though. How can we find stability for a population model that's given by this type? How can we define stability? We remember that we defined equilibrium given by f of x star is equal to 0, right? We said the system is stable if f prime of x star is negative. But this was a qualitative judgment of stability or not stable, right? But we did not quantitatively measure how stable the system is. But do you think that's possible?
It can depend upon how negative that value is. Is that?
Yeah, that's certainly one way, absolutely.
The number of x star values, like the range of x star values over which this is true, that also.
X star is a given equilibrium value.
X star,
What do you
x values.
What do you mean by range of x values over which is stable? I don't understand.
How many values of the driver the system is stable or
the range of, yeah, that's correct. That's what we call resilience, right? Or I think not necessarily resilience. I think but compare related to the idea of resilience. What's the range of values of the driver over which the system is stable, right? And secondly, we can also ask, given the driver value, how much perturbation can the system absorb before transitioning to another state. Okay, so those are other ways of doing it. But let's think about stability using this concept. Remember, what's the meaning of this? It actually measured the modulus of this. Actually told us the return time to equilibrium. Do you remember this is discussion?
Yes.
And in
1
fact,
over f prime.
this was in the first question in the midterm, right? How do you interpret f prime x, right? So it's actually return rate, not return time. Return rate to equilibrium. Okay. So in fact, that was the first question in the midterm exam also, right? Basically, if you make a perturbation around x star, okay, let's call that perturbation y. We showed that y dot is equal to minus of alpha y, where alpha was given by modulus of f prime x star, right? So basically, what does alpha here mean? Alpha is a return comes back to equilibrium from the perturbation, right? And therefore, we can use alpha as somebody suggested in just a few minutes ago as well, as a measure of stability. How quickly you return to the equilibrium can be used as a measure of stability. So this is one measure of stability that people have used for a long time. And in fact, quite frequently used in physics and engineering fields as well. Okay, the value of f, the derivative at the equilibrium modulus, because it gives us return rate to the equilibrium, so it can be taken as a measure of stability. Okay, now let's do the following. Let's do let's do the following plot again. This is the driver, this is the equilibrium. Let's say this is the bifurcation diagram. Okay, now let's look at the stability. Let's call that alpha for the, let's say I'm computing for the upper branch. Okay, let's say what is the value of alpha for different values, for different driver values, but for the upper branch. How do you think this will look like? Any guess? So here, do you think the system is more stable here or more stable here? Where do you think it's more stable?
On the first point.
How about between these two? Say 1, 2, 3. Which is more stable?
1.
1 followed by 2
2
followed
and
by 3, right? So therefore, if you were to now plot alpha, how do you think this will look like as a function of d? Let's call this d2 up to d2, let us say. How do you think this will look like? In fact, it's possible to show that this will, it won't decline in a linear way. I think it does more in a, I think something like this. It actually becomes 0 at this value d2. Okay, I had actually shown this mathematically for the case of the transcritical bifurcation. The pattern also for this model with Hollings type 2 or type 3. Okay, what you will find is that this measure of alpha, this measure of stability, actually reduces and becomes 0 up at this bifurcation point. Okay, so therefore, if we can somehow measure the return rate to equilibrium, okay, we know how stable the ecosystem is. Do you all agree with that? Measuring alpha from data can inform us about stability.
Sir, if the system is not in equilibrium and it's oscillating or is in a chaotic regime, then
So we are we are not doing any of this. We are assuming, given this model is true. Okay, there, there is no chaos possible for this system. If it's chaotic system, the mathematical framework I'm using is wrong anyway.
yes,
I'm looking at a system where bistability is a good approximation and where an equation of the type x dot is equal to f of x is a good approximation. In that system, is this reasonable? So if you can somehow measure alpha, which is the return rate to equilibrium, okay, then it can tell us something about the stability. And if we are comparing two systems, and if alpha alpha is getting closer and closer to 0, what can you conclude?
The transition is going to happen.
Yeah,
The
so it's
collapse.
no, yeah. Okay. Exactly. Okay. So you are more likely to observe a transition. Okay. So now what exactly, just think about the following. What does it mean when the return rate, when the return rate is going to 0? So at this bifurcation point, what's happening to return rate? Return rate is actually going to 0, right? Okay. What does it actually mean? What happens when the return rate to a system is very small or is getting closer and closer to 0?
Unstable equilibrium.
It becomes an unstable equilibrium, right? But in terms of, just think of another measurable quantity. How long does it return? See, rate is inverse of time, right? So if I were to now write on the same graph, plot something called tau, which is the return time instead of return rate, how will the return time look like? The return rate goes to 0. What happens to return time?
It blows up.
It actually increases, right? So return rate increases. The fact that return rate of a system, return time of a system increases as you go towards the bifurcation point, that's called critical point. Sorry, that's called critical slowing down, because it's now very slow to come back, right? System is very slow to come back to equilibrium. And when it goes towards the bifurcation points are also sometimes called critical points. Okay. Therefore, when you're approaching these critical points, system is very slow in its response. And therefore, this entire phenomenon is called critical slowing down. Okay. So that's the point that I think I forgot who mentioned this in the last slide when I was discussing. Okay. So basically, return rate and critical slowing down, measuring return rate is a way of measuring critical slowing down. The system is very slow in response as it's going towards bifurcation points. That's called the critical slowing down. Okay. So basically, if somehow you can measure critical, this alpha, you can make some reasonable guess about the fact that system might be about to undergo a collapse. That's one way of doing it. Okay. Now, are there other ways? Okay. Are there other ways of doing this? Okay. Now let's go back to the potential picture, sort of, to get some intuition. So I wish I had the mathematical formula for potential landscape and I could also plot with you, but you'll have to just trust me when I'm saying these kind of things now, okay? Because I don't have those formula ready to plot. Okay. So we know the formula for the potential landscape now, right? Okay. So this was X, this was driver. Let's say if I plot the potential landscape somewhere here, if I plot the potential landscape somewhere here and somewhere here, do you think their shapes will be different? And if so, in what way?
The hill height will be lowered as we
So
go
we
along.
I have shown you somewhere here, no? In the midway, I
Yes.
had shown it will look like a W, right? Or 2U's, right? How do you think at this extreme it will be? Imagine one extreme where this is just appearing now. How do you think this will look like now? Potential landscape?
A wider valley.
Aha. So no, but we have to justify though. So just
There would be only one valley.
Only one.
So now, how do you think of valley? Is this the width of the valley? Is that right? For this, right? for this
Yes.
equilibrium. For this equilibrium, the width of the valve will be something like this now, right? And in fact, if it's here, it's the entire thing, right? And if I am somewhere here, the width of the valley is very tiny. So let's focus on this equilibrium, the equilibrium with larger value of x. Okay, so if I am at lower values of driver, what do we expect? It will be more like this. Do you agree with this? So the larger vegetation value, let's call that x2. Let's call this branch as x2 branch. Let's call this x1 branch. Okay, this is x1. So somewhere around this point, the region, what we call the basin of attraction, again it was described in the paper, right, will be very tiny, whereas this will be a very big and deep basin of attraction for the larger population value, for this value, right? And now it's now near more or less equal at this point. But if I am now very close to the bifurcation point, how will this look like now? It will be inverse of the first graph, right? How will that look like now? It will be something like this now. Is that right? You all agree with this?
Yes.
Okay, excellent. Okay, now the second, the rest of the features are a bit difficult to show entirely graphically. Okay, so now, and at this point, if I'm here, it's becoming smaller, and the width is smaller is easy to understand. What do you think is happening to the curvature here? As I'm coming from here to here?
It's becoming more linear.
Yeah, it's sort of becoming shallower. Is it reasonable to say?
Yes.
Here there's around the equilibrium there are steep walls, right, on both sides. But when you are closer to the bifurcation value, it will be a much shallower walls nearby, right? So now imagine a ball. Now let's zoom into these parts only. Let's zoom into these parts and plot them here. So this is for D2. And this is for D3. Okay, this is of course my representation. So the ball is rolling here. Okay, let's also assume that there are these environmental perturbations that's kicking the ball in, kicking this ball in this potential landscape, because of which it is going back and forth, right? Okay, now what do you see, the differences in this landscape? What are the differences you see here? This is a steeper landscape, right? This is a shallower one, is that right? Okay, from this, can you infer that the time to return from this?
Yes.
This was also the point that I was trying to make in the previous sort of instance. And to sort of arrive at these potential pictures, you don't even need mathematics, no? You can sort of topologically argue that to go from this kind of a potential in this way is the only way in the end, right? Okay, now what else do you think will happen? This is returning fast to the equilibrium, this is taking longer to the equilibrium. What else do you think will happen? Let's say the system is constantly being kicked around by stochasticity. What else do you think we will observe that is different?
There may be a chance that the ball goes into the other valley, and
let's say it doesn't go. If it goes, the shift has happened. Okay, let's say it doesn't
Yes.
go. It hasn't gone yet.
The oscillation amplitude will be different.
That's a very, very good point, because it's a very steep valley. Imagine the same amount of fluctuations are applied to both of them. Okay, so what's the difference between them? So this will not be able to climb up as much as this one, right? Because it's a shallower well. So therefore this has small amplitude of fluctuations. This has a larger amplitudes. So if you were to visualize this, for example, if I were to just plot x as a function of t here and x as a function of t here, does it make sense? So when you are closer to the bifurcation point, system will show larger amplitude of fluctuations. Do you agree with that? Okay. Okay. Now, is there anything else that you observe? Or is there only two things? Anything else about these two potentials that is different? For this case, if the amplitude is large enough, it might even get kicked out, right, to the other state. Is that right? That's what somebody said. Let's assume it doesn't get kicked out, but let's say the amplitudes are large, the fluctuations are large. Is there some difference between these two that you see?
Maybe the values of u might be different as well.
You see, u is something you can't observe. You only observe x.
Yes.
Right. Okay, so one thing you will notice is the way I have drawn this, if we have a very deep potential within the range of fluctuations, this landscape is symmetric. Symmetric around equilibrium. How about this? Is it symmetric? Again, go back here. Around the equilibrium, does it look symmetric? It has asymmetric structure, right?
Won't that depend on the scale at which you're looking, like how much you magnify?
Yeah, absolutely true. So we're looking at a scale where the shift hasn't happened. Okay. Shift will not happen. Okay. Which means I'm not looking at very large deviations, but still large enough deviations. Somewhere intermediate scales of deviation. If you take any minima, then various small regions around a minima is always symmetric. Okay, very, very large will always be, will always kick you out, right, in this landscape. But somewhere intermediate scale is what I'm looking at. That's an absolutely valid point. Okay, so because of this, how do you think the time series will now differ? In what ways?
As the driver increases, there will be
increase in what? Sorry.
As the driver increases the number of so there will be increased noise in the system, and there will be slowdown.
No, but what about the fact that the potential landscape looks asymmetric here?
The return
the
rate
R-
for either movement to the either sides is different, will be different.
Exactly, right. So here it takes, here on this side it takes a bit, in this case, specific case, on one side the recovery is faster, the other side is the recovery is a bit slower, right? So what do you observe when such a thing happens? How do you think this will manifest in terms of X?
It will be uneven about the mean or whatever the mean.
Right. Basically it will become somewhat skewed around the mean to look something like this. Whereas this will be, on the other hand, if we were to plot, histogram, frequency histogram of X, how do you think this will look like? This will be a symmetric distribution, right? Whereas this will be a
Bimodal.
bimodal is when the shift has happened, right? But the shift hasn't happened, then what do you expect?
Okay, yeah, correct. Sorry. Yes.
Okay, so the typical Gaussian approximation you make for the data, that will become less and less true as we are going towards, you are going towards the bifurcation point. So it's basically symmetric Gaussian, whereas this will be asymmetric non-Gaussian. Okay, now these are all the features that we are just visually quantifying. How do you visually sort of expressing, right? How do you think you can quantify all of this? So how do you quantify fluctuations? How do you quantify return rate? There is something called, there is a method called, autocorrelation function. So you can use autocorrelation function to actually estimate these return rates. Okay, that can help us quantify return rate. How do you quantify fluctuations? Amplitude of fluctuation.
Some variance.
So if you observe an increase in variance, right? X, then you are probably approaching a bifurcation point, right? Okay, now how about this? How can you quantify deviation from symmetry?
The thickness.
There are many ways. There are many metrics. Any measure of asymmetry will do, and the simplest one is typically the skewness or third moment. So variance is second moment, right? Second central moment, right?
Yes.
So this is basically third central moment. Okay, so therefore, if you estimate these quantities, either the return rate from the autocorrelation function, which which is measure of fluctuations, or the skewness in the amplitude of fluctuations. Okay, if you observe that there are these systematic trends, what can you infer? You can observe that you're actually approaching an imminent collapse. Okay, so that's a possible application of these fairly simple ideas that we have discussed in the class. Okay, so what on Friday we will do is to sort of try to do some exercises that actually where you run some simulations and understand this in a bit more depth. Okay, but any questions so far, or was it too much in a single class? Oh, there were a lot of chats actually. It's breaking consistently. It's probably because my internet is very bad.
So these characteristics that we have seen for a
Mhm.
transition,
Mhm.
does it follow for the higher order systems also?
What is a higher order system?
Means where we have more than one species and
Actually, it turns out that several of these ideas continue to hold true there also. Absolutely, yes.
okay.
Yeah, because they all follow from the idea of the critical slowing down. Okay.
Yes.
So what happens, and that critical slowing down is a universal feature of all bifurcations.
Okay. Yes.
Okay. So as long as you have critical slowing down, everything else will basically follow. But although the potential idea is a very specific idea that's useful only for one-dimensional systems.
Yes.
But there is a mathematical analog one can construct for higher dimensional systems. Yeah, it's a great question.
And can you just clarify that how autocorrelation function can help to get that return rate?
Yeah, I can do that, but maybe if anybody else has another questions, I will try to do that first, because that will be slightly more technical.
Okay.
So I can do that. Yeah. After any other questions people may have. Is that fine? Any?
And one more thing,
Mhm.
like I was just wondering that like we consider the environmental perturbations as a Gaussian function, right? And we give that to the system, but the response of the
Mhm.
system turns out to be like where it is operating on, right?
Yeah. Yeah.
So
Yeah.
the input is Gaussian, but the output is not necessarily the Gaussian one that we can infer, right?
Absolutely. Yes. You're right. You're right.
Okay.
You're right. Yeah. You're right. Yeah. So in fact, so although the input is Gaussian, the output becomes non-Gaussian or asymmetric as we go approach critical point. Okay. It's a very important feature. And in fact, it turns out that these rare events become substantially more frequent. Okay. And therefore, the distribution of those rare events actually becomes what's called a power law at at these critical points. Not in all critical points, but in some type of critical points.
Okay.
Value symmetries where system changes from one type of stable state to another type of stable state. Okay, and that's something that physicists have studied, and a lot of disciplines have used those ideas in biology as well.
I was wondering, is it safe to say that if systems approach collapse, they become more noisy?
That's one prediction of these mathematical models. They become more of course it depends on what do you mean by more noisy.
Like just increase in variance or something?
Basically, the characteristics of noise become larger. Measures of noise like variance, first, second, third moment all become noisy. So why is it? Just think about it. Why it's interesting? Just think about the following. If you now go back to this diagram, right? This diagram says that the mean is decreasing as a function of driver, right? Mean is decreasing, and suddenly there's a collapse, right? But what these are telling is that as you are getting closer and closer, not only mean but even the higher moments are also beginning to increase, and they increase in a very rapid way. Okay, and therefore you can don't just rely on the mean value of your state variable. You remember, as mean is often the sort of thing that we always measure in biology, right? And variance is sort of thing that we measure to uh, is something we try to minimize, right? To get better measurement of mean. But what this is saying is that actually that measurement of variance itself is interesting here. That has information about how stable the system is, or rather how lack of stability rather in this specific case. Is that it? So if there are no other questions, I can take up the question on autocorrelation function. Okay. So how first of all, I need to don't know what is an autocorrelation function, right? So think of, you have some measurement of population density or any signal, okay, as a function of time. Okay, something as a function of time. So what is autocorrelation function? So now, before we go there, now consider two very close by values of time. Okay, let's call that t and t plus delta t. Okay, if this delta t is very, very small, how do you think, what is the similarity? Just think of the concept of similarity. How similar do you think the values of x will be between these 2 points as they become closer and closer? They will be more and more similar, right? Okay, so basically correlation is a measure of that similarity. Okay, so what is autocorrelation? Autocorrelation, usually when we think of correlation, we think of correlation between two different quantities. Okay, but autocorrelation basically is correlation between same quantity x, but they are separated by time. So I consider value of x at time t, and I consider value of x at time t, like t plus delta t, and I look at the correlation between these two values. So, and more similar they are, this number will be closer to 1. X were series of random numbers. Okay. How do you think this will look like? What will be the correlation between t and t plus delta t, however small they might be?
Zero.
It will be 0, right? If it's a random set of numbers. Okay. So the basic idea of the autocorrelation function is as follows. So let's call this autocorrelation function t. See, it depends on this delta t, right? The time lag I have chosen between. So I have chosen 2 time steps. I want to compare how similar my state variable population. It could be some signal that I'm interested in measuring. How similar they are, which are separated by tau, delta t time apart. If it's very, very long time, how do you think? If I separate these two very, very long, for a very, very long time, what will the correlation be between the two?
Very less.
You expect this to be less. Okay. So there are, of course, some funny cases where they become opposite. But if you wait for two very long time, the same quantity has changed sufficiently over time. So therefore, you expect that this will be close to 0, right? If if it's very close, let's take the limit of delta t is equal to 0. What will that value be? It will be when 1, right? It's a value with itself. The correlation of x with itself at the same time. That will be 1, right? So the maximum value it can take is 1 if they are highly similar, right? So now in between, what do you expect? It will decay. It will decay to 0 in some form. Okay, at large time scales. Okay, so this is called the autocorrelation function. Now you can see how rapidly this function is, decaying to 0. Okay, so the scale or time scale basically, time scale by which x becomes uncorrelated with itself. Okay, what will that be? Somewhere here, no? Let's call that tau. Okay, time scale by which x becomes uncorrelated with itself is called tau, so called the autocorrelation time. So do you all agree with this now? The system, it's something like you can also think of the following. If you are looking at very t plus delta t inverse x of t, if delta t is very small, but larger it becomes the delta t. I don't remember what happened long back, right? So a system that has lost the memory of itself, and the time scale over which that memory is lost is called the autocorrelation time. So let's think of it in an abstract way. Okay. So if you have any signal, you can compute this autocorrelation function and compute this tau. Tau is measure of how system forgets itself, how time scale over which system forgets itself. Is that fine? So are all of you clear now what this autocorrelation time means? Let me know.
Yes, sir.
Okay, now think of the following. Think of a ball rolling in this and a ball rolling in something like this. Okay. In which of the two systems tau is, let's call this tau 1, let's call this tau 2. Of course, let's assume there is fluctuations. System is basically jiggling around this minima. Okay. Which of them will have a larger value?
Tau 2.
Tau 2. Why?
Because it will be slow in dynamics.
It takes a lot of time to come back. So say I make a perturbation now, right?
Yes.
It takes a lot of time to come back. Here, if I make a same perturbation, just comes back quickly because it's very steep. Meaning the perturbation that I made. So that basically, if I make some perturbation, if it comes back to equilibrium, I have forgotten the perturbation now, right? Basically, that's one way to think about this, right? So time it takes to reach the equilibrium can be thought of is basically you can will be similar to the autocorrelation time, right? So tau 1 will be much less than tau 2. Is that right? The time to equilibrium is a measure of autocorrelation time, and therefore our is the system's recovery time. Does it make sense now? How they are connected?
So we can't hear you for the last sentence.
So all that I was trying to say was, you yourself agreed that there is a connection between so how the memory, how long does the system take to
Yes.
lose its memory? This tau 1 is much less than tau 2. Therefore, tau 2 has a longer memory compared to tau 1, right?
Yes.
And we also know that this system has more stability compared to this system. We also know this has the critical slowing down. This doesn't have critical slowing down, right? So therefore, by measuring autocorrelation time, I can measure the stability of ecosystems. Does it make sense? That's the connection.
And can we say something about that asymmetry that we were like previously talking about?
But is this point clear now? At least autocorrelation part, is it clear?
Yes.
Okay.
So here only if we have asymmetric valley, then
in this case.
yes.
So usually autocorrelation functions cannot measure non-linearities. Well, asymmetry comes from non-linearities in the systems. Okay. Autocorrelation function is doesn't do a very good job of measuring those. But you're right. In principle, it's possible to look at autocorrelation time for perturbations from the left side and the right side and compare them. It's also possible. It's possible to do, but I haven't seen anybody do that actually.
Okay.
I described variance and skewness. I think that's probably sufficient. I think. Any other questions? Okay, so there are no questions. We'll meet again on Friday.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Bye.